Okay, so welcome to this new lecture. In the last lecture, we started with the defect chemistry and defect equilibria in ionic solids or in electroceramics. So, there we introduced the concept of defects. There are various kind of point defects such as vacancies, interstitial, substitution ions, etc. And then we introduced the Kroger-Wink notations, where each defect, whether charged or uncharged, has a particular notation by which it is denoted. In the nutshell, if a defect is positively charged, then it is denoted by a dot on top of it. So, for example, if in case of oxygen vacancy, you write it VO double dot if it is completely ionized, and we will in this course we will assume that all the defects are completely ionized. And if it is a negatively charged defect such as metal vacancy, then it would have a dash. One dash would mean single charge and two dash would mean double charge, and so on and so forth. And then we looked at various defect reactions. First of all, the rules which govern the formation of defect reactions. So, basically what it means is that formation of defects can be interpreted via a reaction, just like a chemical reaction. The thermodynamic basis we will establish a little later, but so if you write them like a chemical reaction, then what you have to do is that you have to maintain the site balance, mass balance has to be preserved, and also since the solid is electrically neutral, the electrical neutrality has to be preserved. And in this case, since we are treating oxides as the main materials in this defect chemistry module, we will treat oxygen vacancy as VO double dot, assuming that it is completely ionized, and a metal vacancy, if metal was M2 plus, then it would be VM double dash if it was completely ionized. If the valence of metal is different, then it would be VM single dash or triple dash or 4 dash, depending on the valence of the material. And then we looked at what are the defects in stoichiometric solids, assuming the case of MO as stoichiometric solid. So, the first important defect is Schottky defect. Schottky defect is nothing but formation of a metal and oxygen vacancy, simultaneous formation. This does not disturb the stoichiometry of the material. So basically you have a pair of two vacancies in a given solid. Of course, the relative proportion of these vacancies will change if if you had materials like Al2O3 or TiO2. So, that I would leave it to you to work out, but make sure that you maintain the charge and site balance there. And another kind of important defect is Wrinkle defect. Wrinkle defect is formation of either a metal interstitial coupled with formation of metal vacancy, complementary metal vacancy, or in case of anti-Wrinkle, it is formation of oxygen interstitial complemented by an oxygen vacancy. So, these are the two most common defects that occur in stoichiometric solids. And third is intrinsic ionization, which is nothing but excitation of electrons from the valence band to conduction band, giving rise to a electron hole pair, and this can occur in any material. And then we looked at defect in the stoichiometric non-stoichiometric solids. In reality, what happens is that most of these materials operate either at high oxygen pressure or low oxygen pressure, and depending upon the operating conditions, they are often non-stoichiometric. So, there are two basic types. One is oxygen deficient or metal excess, which is denoted as MO1 minus X or M1 minus YO, and second type is oxygen excess or metal deficient, and this is written as either MO1 plus X or M1 minus Y. Sorry, in the previous case it would be M1 plus YO, and in this case it would be MO1 plus X or M1 minus YO. And then we took various cases for starting with oxygen deficient or metal excess oxides, and the case 1 was where we took oxygen vacancies as dominating defect, and we established how the defects can be formed. You can have electronic compensation of defects or you can have ionic compensation. Basically, in both of these cases you will have formation of oxygen vacancy coupled with either formation of electrons, quasi free electrons, or reduction of metal vacancy, metal on metal site. And then we looked at the case when metal interstitials dominate, and in that case the formula would be, for example, in this case we have taken MO2. So, here it would be M1 plus YO2, and as a result, so here since metal is +4 vacancy, the metal will form an interstitial followed by complemented by reduction of metal on the metal side, or if it was electronic compensation, then it would give rise to 4 electrons. So, the difference in two cases is number of electrons created, relative proportion of two defects, and examples of such cases could be n-type conductors materials such as TiO2, zirconium oxide, cerium oxide, Nb2O5. So, now we will look at the case of metal deficient oxides. So, we will start with in case of metal deficient oxides, as you can guess intuitively, it would be either metal vacancies or oxygen interstitial if it was excess oxygen in case of excess oxide. So, metal deficient would in this case be another case of oxygen excess, and formation in this case typically happens at the surface. We will deal with two cases. The first case is case 1 is when metal vacancies are dominating defects. So, in this case we represent the oxide. So, we write the material as the formula is M1 minus YO, as we have seen earlier, and if it was MO, if it was M2O or MO2, then it would be different, of course, and where Y represents the extent of non-stoichiometry, and the possible defect reaction that would occur is, so defect reaction would be, so you have, since it is a case of metal deficiency, so you have oxygen coming out, oxygen coming in, oxygen goes to oxygen site, but if it was, so we are taking the case of MO type, which means for now you have to maintain the site balance. So, you create one oxygen site where the oxygen goes, complementing that you have to have a metal site, but since this is a metal deficient oxide, you will have vacancy of metal. Now, this vacancy of metal, since it is a MO form, it would be doubly negatively charged, double negative charges. Now, this can be complemented in this case for example, by formation of two holes. So, this is your electronic compensation. So, basically you have creation of holes, and as a result of creation of holes, just like in the previous case, this forms a p-type conductor, and examples of materials which show this characteristic would be your materials like NiO, FeO, COO, etc. So, most of these transition metal oxides, they show this characteristic. Now, this is electronic compensation, right. If you have ionic compensation, this would mean half O2, OO, complementary metal site which is vacant. Now, unlike in the previous case where metal reduction occurred, here you may have metal oxidation. So, metal on metal site, if it was oxidizing to plus extra +1 state, then this would be 2 mm dash. So, basically what it effectively means is that this is equal to 2 of M3 plus. So, metals, so basically what it means is that oxidation of M2 plus to M3 plus. Now, you can also have from M2 plus to M4 plus, in that case only one side will be oxidized. So, this is the basis of ionic compensation of electronic compensation in these materials. Now, typically what you will find, these materials are susceptible to having extra holes. So, metal vacancy is often complemented by creation of extra holes, giving rise to a p-type conduction behavior in these materials. Now, we will take the second case. Second case is when you can have oxygen interstitial as dominating defect. So, in this case what happens is that, now how do you represent these materials? So, formula would be MO2 plus X, since you have extra oxygen, and so extra oxygen in another way means you have deficiency of metal, and the way these this happens is half O2. So, here the oxygen does not go to oxygen site, rather it goes to interstitial site. So, it goes, if it goes to interstitial site, you do not need to create any kind of vacancy. If it goes to interstitial site and if it is completely ionized, it will have two double dashes, OI double dash plus formation of two holes. So, this would be your, again this would give rise to p type conductors. I am choosing whether it is MO or MO2 based on the cases in which each of these defects are observed. So, the choice of, so the basis of choosing whether MO or MO2 for particular case is entirely based upon type of materials which show this behavior. An example is like UO2 plus X, which is uranium oxide. So, again this is your electronic compensation. Ionic compensation would again mean oxidation of metal. So, in principle it is also possible. So, ionic compensation would mean plus dot. So, two of the metal sites will be oxidized, but again as I said, in both of these cases the materials prefer to have prefer to be in the form of p-type conductors by creation of extra holes. So, this is the basis for formation of defects in non-stoichiometric oxides. So, we have discussed two of these cases and looked at the examples, whether it is oxygen excess or oxygen deficient. Now, not only you can have defects created by as a result of Schottky or Frenkel defect formation or electronic disorder formation, you can also have as we saw, because of deficiency or excess of oxygen or metal, you can also form defects by dissolving impurities in these materials. Most of these materials, most of these ceramic materials, they tend to contain some amount of impurity in them depending upon their nature and their structure. Impurity incorporation often is governed by the size of interstices that you might have, the size of ion which is coming inside the host lattice, etc. So, but if you look at, for example, most of the refractory oxides, none of them is available in extremely pure form, and also it is very difficult to, it is commercially economically very expensive to fabricate these materials in ultra pure form. So, as a result, they tend to have some sort of impurities in them. So, most of these impurities, when they are present in the host lattice, they also give rise to complementary defects. So, we will discuss this as this part as dissolution of you can say impurities, whether intentional or unintentional, or foreign cations, assuming that most of these impurities are oxides as well, in an oxide. So, here we will so you can have various kind of, so possibilities are various. So, for example, host material would be of MO type. So, now if you have impurities, now impurities can be BO or B2O3 or B2O or BO2 and so on and so forth. Now, if it was in substitutional impurity, which means B replaces M on the metal side, in that case you do not have any problem. Oxygen occupies the oxygen side and B occupies the metal side, given that if their sizes are not too different. If the sizes were too different, then the host lattice does not accept the impurity that readily. As a result, the impurity is present as a solid chunk of impurity inside the material than substituting, because it gives rise to massive strain in the lattice, and it is not. But however, if the sizes were equivalent, then BO in MO, no defects, because the valence of B and valence of M are equal. However, when you have replacement of if you have dissolution of impurities in the form of B2O3 or B2O or VO2, in this case the cation which is coming into the host lattice has a different valence, and these are called as aliovalent ions. In previous case it would be called as isovalent, in the previous case it would be aliovalent. So, no defects, because in the previous case the you won't form any defects because of isovalent impurity. However, when you have aliovalent, impurity, what it means is that impurity of different valence, and by which you basically mean cation, because oxygen, if you consider impurity as an oxide, oxygen has same valence as oxygen, so there is no problem there, but cation has profound effect on the type of defects that you will create. So, let us take the case of dissolution of. So, suppose here we take example. So, the parent oxide or the host oxide is MO, and the foreign oxide is let us say in this case A2O3. So, what are the scenarios which are possible? You can have various scenarios. For example, if you have now in these cases, what will happen is A will typically go to M site. So, as a result, you will have either creation of some of the metal vacant sites, or you will have creation of some other charges. So, let us see what these things are. So, let us say first is case 1. So, in this case, the first case is, let us say the impurity atom A goes to the metal site. So, what it do? So, you have dissolution of case 1 is A goes to M site, and so let us say what it happens is here. So, A2O3 going into MO lattice, let us say both of A go to M site. Now, both of the A's have gone to M site. What it means is that the valence of A is +3, valence of M is +2. As a result, the A which is going to M site is going to have extra +1 charge, which is denoted by a dot. So, 2 AM dot plus, let us say, since 2 A's are going to 2 M sites, the to maintain the site and mass balance, 2 of the 3 oxygens here go to oxygen site. So, which means they maintain the site balance of MO, which is the parent lattice. Extra oxygen goes out, half O2. So, extra oxygen does not stay inside. So, this is balanced in terms of mass and site, but how about the charges, the electrical neutrality? You have now +2 charges here. These +2 charges have to be compensated. So, these 2 charges here are compensated by creation of 2 electrons. So, this is your electronic compensation and giving rise to quasi-free electrons. So, this is case 1. Case 2. Now, here again you have A going to A site, but in this case all the 3 oxygens occupy oxygen site. So, let us see what happens here. So, A2O3, so both the A's go to M site having 1 positive charge at each site, plus all 3 oxygens go to oxygen site. Now, both the A's have gone to M site, all the 3 oxygens have gone to oxygen site. So, mass balance is fine, but what about the site balance? Parent lattice has one M site for O site. Now, here you have created 3 O sites. So, for three of these O sites you need to have 3 of M sites, and you are filling only 2 of them, which means one of the O sites which is created as a result of 3 oxygens going to oxygen sites, you will have one metal site which would be vacant. So, you will have Vm having 2 negative charges. So, now this is balanced site and mass wise as well as charge wise. So, this is another possibility that could happen in these when you put A2O3 impurity in MO solid. So, these are 2 cases when you have dissolution of foreign oxide into a host oxide of MO type, let us say. Now, you can also have other scenarios. Other scenario, for example, is suppose the parent oxide was oxygen deficient to begin with. So, here assume that the parent oxide is oxygen deficient. It already had oxygen deficiency. So, then what? Now, you have A2O3 going into the MO lattice, plus you had VOs present there. Now, what is going to happen to these VOs? So, both the metals so you had 2 A's go to M site. Now, what? Since you had 1 oxygen site already vacant and you are going to create 2 for these, all the 3 oxygens occupy oxygen site. So, now what has happened is the oxygen vacancy which was present in the solid to begin with has taken care for 1 extra oxygen. As a result, you do not create any other defect in the material. So, this would be case 3. So, here it is balanced site wise as well as you have charge wise valence as well. You have 2 positive charges on the left and 2 positive charges on the right. And you can take case 4. Case 4 would be assuming that MO already is of P type, which means it already has lot of holes inside it. So, how do you do now? So, you have A2O3 A2O3 plus some holes were present. Let us say I am going to balance this reaction later on. So, both the A's go to M site, 2 positive charges. Now, here in this case what happens is, since you had already holes present, and let us say 2 OOs and half O2, one of the extra oxygen goes out, since you have to maintain the side balance. So, here I do not create any defect on this side, all I do is that I make it 2H plus just to balance it electronically, and now you also have side balance, and this is another kind of reaction that would be possible if the material was of p type to begin with. So, in the previous slide we looked at when the material was stoichiometric, it did not have any defect to begin with. Then what is the scenario? So, you can have creation of a metal vacancy or creation of 2 extra electrons, or alternatively if the metal was already oxygen deficient or contained holes to begin with, then these holes or oxygen vacancies could be compensated by presence of these impurities. So, as a homework you can do, for example, as an exercise you can discuss dissolution of A2O in MO and understand the defect formation So, this I will leave it to you to work out yourself, and that will make it clear what happens when you put oxides of different valence in parent lattice. So, I will just leave it to you at the moment. The solution of this I will provide, these will be provided in extra sheets, or some reference will be provided for these if you want to go through them. So, so this has established, so far what we have seen is how the defects, what kind of defects are there, how they are formed in stoichiometric solids, how the defects are formed in non-stoichiometric solids, where you have either metal deficiency or oxygen excess, or metal excess or oxygen deficiency, and what happens when you dissolve either intentionally or unintentionally an impurity which is typically an oxide in a parent lattice, and this particular material, impurity material, has different valence cations as compared to the host lattice. So, I hope that now it is clear how the defects are formed, but the question now is, I said in the beginning of the lecture that these defects are present in the solid thermodynamically, but the question now arises, what is the equilibrium concentration for these defects? How can we work it out? There is a thermodynamic basis by which we can work out the equilibrium concentration of these defects, especially the intrinsic defects. Now, here we are going to talk about intrinsic defects. You have two kind of defect. One is intrinsic defect, which is the defect which is created as a result of either non-stoichiometry of the solid or Schottky or Frenkel defects. Second type of defect is extrinsic defect, which is created as a result of impurity incorporation in the material. So, these two are two different cases. So, here we will look at what is the equilibrium concentration of intrinsic defects in a given material. So, what we will do is that concentration of intrinsic defects. So, let us consider with the for example, formation of let us say Frenkel defect in a material Mx. So, the material we take is of Mx type, which means M and X valencies are same, and let us say the dominating defect is Wrinkle defect. So, if it was a Wrinkle defect, then I can write this as MM plus XX as Mi plus Vm plus Xx. So, you have site balance because you have one anion site and one cation site. You have charge valence, the interstitial carrying two charges is balanced by two negative charges on the metal vacancy side. So, this is your defect reaction. Now, when you form the defects, what happens thermodynamically? Thermodynamically, the system had a free energy before the defects were formed. Okay. So, imagine the crystal having no defects, it has certain free energy. Now, defects want to form. Once the defect form, there is a free energy change associated with that. So, and each defect is going to have its own energy formation. Okay, you need to spend some energy in forming the defect. So, what is that energy balance? So, let us say if you form number of defects that are formed are n, and the energy expense per defect, let us say, is delta Gf. Okay. So, basically per defect pair you can say, because here you are going to form a pair. So, the moment you form metal interstitial, you have metal vacancy. So, energy expense per pair is defect pair is delta Gf. So, what is the net free energy change? So, delta G from a 0 defect state to, let us say, n defect state is equal to G minus G naught. G naught is the defect free state. So, this would be n delta Gf. So, this is your enthalpy change minus at a given temperature, at that particular temperature, we are assuming that here temperature and pressure are constant. At this particular temperature, what is the change in the entropy? Because the moment you create the defects inside a material, you are going to lead to is going to lead to change in the configurational entropy, which is delta Sc, and which is going to be a positive quantity, because you are going to introduce defects, which means you introduce the disorder inside the material, and as the disorder increases, the entropy always increases. So, this is what is the basic thermodynamic free energy change that is going to happen when you form n Frenkel defect pairs, each defect pair having energy of formation of delta Gf and minus of the entropy term, which is a positive term because of increase in the entropy. Now, when you plot this delta G, which is going to happen with respect to n. So, how do you why we are going to do this? We are going to do this because we want to find out what is the equilibrium concentration. Now, equilibrium concentration will be achieved when this free energy change will be minimum. You can keep forming defects. Let us say you form n1 defects, n2 defects, n3 defects, n4 defects, etc., etc. Now, all these concentrations are not going to be stable. Only one particular concentration is going to be stable, at which delta G is going to be minimum. So, the plot of delta G, if you plot delta G versus n, let us say the n defects, is going to be something like this. You can simulate this graph as well, and this minima will correspond to equilibrium concentration, because here this change in free energy would be maximum, which means the free energy of the crystal after formation of these many defects will be minimum. So, what we now need to do is that we need to differentiate that particular equation which we wrote in the previous slide with respect to n and find out what is the equilibrium concentration of defects. So, let us do that. So, now to do that, first we need to work out what is the change in entropy. Change in entropy can be written as delta SC can be written as K ln W, where K is nothing but your Boltzmann constant and W is nothing but number of ways in which defects can be arranged inside the solid on these lattice sites. So, the moment you put defects, you can put defect in the way you want it, but what is the optimum way? So, and of course, there are going to be many different possible ways. So, let us work out what is the number of ways in which you can put these defects on the metal sites. Sorry, on the atomic sites or in the lattice. So, let us say now when you form these Frenkel defects. So, Frenkel defect would mean you have metal vacancy and you have metal interstitial. Now, let us say we are saying total number of defect is equal to n. This is going to be equal to number of vacancies NV and this is going to be equal to number of interstitial which is Ni. So, just by equality and just by looking at the defect reaction itself, this is very simple. So, number of Frenkel defect pairs N is equal to number of metal vacancies and number of metal interstitials. So, now assume that total number of lattice sites is equal to capital N. So, in this case, if these are the numbers which you have, what is the number of possible ways in which you can arrange the vacancies? So, let us say number of possible ways to arrange the vacancies, let us say that is written as WV. Okay. So, WV is given as factorial n divided by n minus n NV factorial multiplied by NV factorial. So, this is your WV. Now, similarly, what is the number of possible ways to arrange the interstitials? So, in case of interstitials, we can define this as Wi, and this Wi is again given as, since you have similar number of interstitials and vacancies, this would be n factorial divided by capital N minus Ni factorial multiplied by Ni factorial. So, this we have so far worked out individual ways for arranging vacancies as well as interstitial. So, what is the total number of configurations? We defined that as W, and this is nothing but product of Wi into WV. So, as a result we can work out what is the entropy change. The entropy change is delta SC, that is equal to K ln multiplied by n factorial divided by n minus n I factorial into n I factorial, and again n minus n v factorial into n v factorial. Now, since we know that n v is equal to n I, so we can write this as it would be 2 k ln n factorial is equal to n. We can write this as n minus n factorial into n factorial. Okay. Now, to solve this log of factorials, you need to use Stirling's approximation. So, which is Stirling's approximation is nothing but, if you have ln n factorial, then this would be n ln n minus n. So, if you apply this to our equation, what you can work out is delta SC would be equal to 2 k n ln n minus of n minus n ln n minus n minus of small n into ln small n. So, this is the expression that you work out after working out both W I and W V, and then eventually W, and substitute in the expression for change in the entropy. So, so now the net free energy change, so the total free energy change that we wrote earlier, delta G, that would now be equal to n delta G F, okay, this is the first term, minus of T into 2 k into capital N ln n minus capital N minus small n ln capital N minus small n minus of small n ln n. So, this is your expression for free energy. So, this delta G, now you can write it as n delta G F minus of 2 k T into n. If you can rearrange, if you rearrange these, what you will get is n ln n divided by n minus small n plus small n into ln of n minus small n divided by small n. This is what you are going to get if you do it, if you rearrange these. Okay, that is very simple. You can just need to open this up. So, that will give you the form. So, if you just do this n ln n minus n ln n minus n. So, you can take the n out, make it ln n divided by n minus n, and this would become plus. So, plus n ln n minus n minus small n ln small n. So, you take out small n, and then this would become ln of small n minus small n divided by small n. So, this is very simple to do. Now, at equilibrium, we have already talked about the equilibrium. At equilibrium, concentration of defects, we can say del of delta G del n at constant temperature and pressure is equal to 0. and we can also assume, since number of defects in the solid are going to be much smaller than the number of lattice sites, we can say since and n is very small as compared to n. So, n minus a small n is almost equal to capital N, and that you will see when we calculate these numbers. So, using these two formalisms, now you can simplify this equation further. So, when you differentiate, what you will find is this. So, if you do that exercise and replace capital N minus small n to be equal to almost equal to capital N, then you will find as small n. So, this would lead to, so if we differentiate the free energy equation with respect to n, this would lead to, it's a very simple differentiation. So, this would lead to exponential of minus delta Gf divided by 2 k T. So, this is an important expression. So, watch this, what this tells you is that, so vacancies, formation of vacancies is exponential function of energy expense per pair and temperature, and as you can see now here, as the temperature increases, this number will increase, and as this number increases, this number will decrease. It is going to be much harder to form defect when you have low temperature and higher energy expense. Now, this delta Gf can further be broken into delta Hf minus T delta Sv. So, this delta Hf is nothing but your enthalpy of defect formation, and delta Sv is nothing but, so earlier we took the configurational entropy change, this would be your vibrational entropy change. Okay. So, if you plug this in above equation, so as a result small n by capital N will simplify to exponential of minus of delta Hf minus of T delta Sv divided by 2 kT, and this can further be equal to exponential of delta Sv by 2k multiplied by exponential of minus delta Hf by kt. Now, in most cases what happens is this entropy change is very small. So, this term is often neglected. So, since delta Sv is often very small or negligible, so exponential of delta Sv divided by 2k is almost equal to 1. So, n by n is equal to exponential of minus delta Hf by 2 kt. So, this is your standard expression to calculate the equilibrium concentration of defect in a ceramic material or in an ionic solid. Now, this expression tells you that n is an exponential function of temperature and enthalpy of formation. So, you can write, so as temperature increases, n increases, and as delta Hf increases, n decreases. So, what you will see is that most of these ceramic materials, they have appreciable intrinsic appreciable intrinsic defect concentration at higher temperatures. At lower temperatures, they do not contain significantly larger number of defects. Similarly, delta Hf is enthalpy of defect formation. So, which you can guess that a delta HF is nothing but ease of defect formation, represents the ease of defect formation. So, of course, materials with higher bond strengths are going to be find it much more difficult to form defects, and and similarly materials with higher temperature, they will have higher melting points, they will have at one temperature lower defect concentration as compared to those with lower melting points, because melting points are related to bond energies. For example, you can make comparison between magnesium oxide and sodium chloride. Sodium chloride is a material with so for instance, you can make a compare NaCl and MgO. So, MgO delta HF is almost equal to 2.4 electron volt, and in this case it is 7.7 electron volt, and this is directly related to Tm. So, Tm of NaCl is about 802 degrees centigrade. In case of MgO, it is about 28-25 degrees centigrade, and these are, so you can see that MgO being a larger melting point compound, because of larger bond energy, it has larger enthalpy of defect formation. So, as a result, intrinsic defect concentration in MgO, so at a given temperature, number of defects in MgO is much smaller than in NaCl, and this is because of higher defect formation energy in MgO as a result of higher bond energy. So, however, if you scale it to same homologous temperature, then defect concentrations can be almost comparable. So, at same homologous temperature, of course, below the melting point of NaCl, so you can find that NaCl will have roughly 2 ppm defects and MgO will have approximately 0.4 ppm. So, they are more comparable when you talk about same homologous temperature, but the point here is the effect of bond energies and the temperature. And however, so these defects are, this is intrinsic defects. Now, in the previous expression we worked out this expression for Frenkel defects. Similar expression can also be worked out for Schottky defects, because there also you have pair of defects. So, there is no difference. So, the only thing is that this will become delta HS in Schottky defects. So, when we talk about NaCl and MgO, its delta HF is nothing but for Schottky defect, because both of the materials are prone to having Schottky defects. However, the derivation remains same and there is no change. So, we'll take up the we'll finish here, and we will take up the defect equilibria and what is the thermodynamic basis of treating defect reactions in the next class. Thank you.